what we're going to talk about today is something called the integral test. The integral test is something we've actually been implicitly using, even though we haven't explicitly stated it as a theorem. And it's a very useful way to actually know whether or not a series of positive terms
actually converges.
So integral test. Given a sequence AN and a continuous decreasing function that recovers this sequence So I'll draw the picture in a second, which will clarify everything. Then this series, n equals 1 to infinity, an converges if and only if. So I'm going to write this like this. So the statement that this series converges implies that the integral from 1 to infinity of this function converges, and conversely, this function converges implies this sequence converges. Okay, and we've kind of seen this already for specific sequences. That's how we saw, for example, that the series 1 over n doesn't actually converge. Yeah? But it turns out that it's true in general. So this is the picture. We have a sequence of terms like this. So we think of the series as being the area of these individual blocks, right? As we've done many times. So this is A1. This is A2. A3. So the area of all of these blocks summed together is exactly this quantity. Yeah? And if we have a function here that recovers this sequence, let's draw what that means on this picture. Well, here we are at 1, here we are at 2, here we are at 3, here we are at 4, and so on, right? So if f1 is equal to a1, that means it goes through this point, yeah? If f2 is equal to a2, then it goes through this point. If f3 is equal to a3, then we go through this point, and so on, and so on, and so on. So this function does something like this. That's what this function does, yeah? So this is our function f. So this picture represents this information. Right? This information here is exactly this picture. This is just writing in the language of words and of maths what this picture says. Yeah? This is the real meaning of it. Yeah? And then what's the statement? What's the conclusion? The conclusion is that the convergence of this series is equivalent to the convergence of this series. So this will happen if and only if this happens. And this is very useful because that means in order to determine if a series actually converges, we just need to find a function f that recovers it, okay, and then integrate that thing. And integrating something is something we have great technology to actually do. We have the fundamental theorem of calculus that puts us in a position to use these powerful tools that we've learned. Yeah. So why is this the case? Well, one part of this is pretty straightforward from this picture. If we have this thing, I should complete the sentence, converges. If this thing converges, this exactly says that the area underneath this function f is finite from 1 to infinity. Yeah, that's exactly the meaning. And we can see that these blocks are all underneath the graph of this function. Yeah, so if the area underneath the graph of this function from 1 to infinity is finite, yeah, then for sure, if we add together all the areas of all these blocks from 1 to infinity, that too is finite. Yeah? So it will indeed be the case that this thing converges implies this. This is just immediate from the picture. Do you see what I mean? Okay, I'm only seeing thumbs up, so I assume that's okay. So this implication So the fact integral from 1 to infinity f of x dx converges implies this series converges is just from the picture. Okay, now to see the other way around, the fact that this thing converges implies that this function converges, we have to draw a slightly different picture. Okay, we have to draw a slightly different picture because in that case, what we want to do is somehow to have that the function is underneath all of these blocks. The graph of the function is underneath the blocks. Yeah, but the way it's set up, that's not true, right? However, we can just change things around just a little bit. So look, if we define a function, put it here, define function g of x to be equal to f of x plus 1. That's just moving the function along by 1. Yeah? Let's see what this function g of x is like. So g of 1 is equal to f of 2. Yeah? And f of 2 is here, so g of 1 will be right here. Yeah? Give me the thumbs up if you're with me. Okay. G of 2 is equal to f of 3. So g of 2 is f of 3, which is at this height, so this is where we are. Yeah? G of 3 is equal to f of 4. F of 4 is this height, yeah? And so this is where g of 3 is. Yeah? And you can see what's happening. So this function g, so it's also going to be decreasing. Since f is decreasing, it's just shifted along by 1, goes down like this. Yeah? So this function g is indeed underneath all of our blocks. Yeah? Cool. So since it's underneath all of our blocks, then it's immediate that the following is true. So also see that if the sum from k equals 1 to infinity ak converges, then the integral from 1 to infinity g of x dx converges. Yeah, it's definitely true, huh? We just see it. It's from the picture. Again, from the picture. Yeah? But what is this thing? This thing is nothing but just f shifted forward. So the integral from 1 to infinity f of x plus 1 dx converges. But then we can just do a change of variable and let u be x plus 1. And then this integral, let's call this thing star, is equal to the integral from 2 to infinity f of u du. In other words, it's the area of the graph from 2 to infinity of our function f, which I'm going to put here. So it's this area. Yeah? But if that area from 2 to infinity is finite, then for sure the integral converges because the only other part is the integral from 1 to 2, and that thing for sure is finite because it's a nice continuous decreasing function, so there's no problem, right? It's always less than its value at f of 1. So whatever's happening between 1 and 2, that's not gonna mess anything up. That thing has got finite area. So if we know that the area from 2 to infinity is finite, then the entire integral from 1 to infinity converges. Yeah? In fact, if we think a little bit longer, it doesn't matter where we start. If the integral from any number a to infinity converges, then the entire thing converges. Because the only thing that goes wrong is when as we let the interval from a to r, where r goes to infinity, get bigger and bigger and bigger, that thing blows up with respect to the length of that interval. Yeah, and so we can start from any point and still have that the integral converges from 1 to infinity if it converges from A to infinity. All right, so this theorem is nothing difficult. This is just a picture. We just look at this thing, this function f, to get one side of this implication, to get the implication that this implies this, and all we do is draw another thing on this picture, just the function f of x plus 1, which is shifted underneath, to get the other side of the implication, this implies this. Yeah, nothing difficult, nothing complicated, nothing to be believed, nothing mysterious, just pictures. Like everything in this course, every concept, every fact, which we call a theorem, it's just coming from a natural, simple picture, which we have when we draw the information, the hypotheses of the theorem. When we draw it, we see the conclusion in front of us if we look a little bit closely. Yeah? Cool. Now we have this. We believe it. We can use it. And it turns out to be very useful. Okay. Example 1. N equals 1 to infinity, 1 over n squared plus 1. Does this converge? Okay. What do you people think? Perfect, perfect, perfect. Yeah. So what you just did was as following. You said, okay, 1 over n squared plus 1 is less than 1 over n squared, and 1 over n squared is recovered by the function 1 over x squared, and the integral of 1 over x squared is finite. Yeah, that integral converges. That was your chain of thought. Yeah, which is a totally valid way to do things. I would be completely happy with that. The solution in the book, though, follows more closely the actual statement of using this integral test for series, which is to find a function that exactly recovers this guy. So what function exactly recovers that guy? What function would do it for us? Perfect, yeah. Right, and since it's only asking if this thing converges, yeah, then we just have to think about the convergence of this guy, and arguing exactly as you did, this guy is underneath the graph of 1 over x squared, so we know it does converge. But if we didn't do that, if we wanted to just integrate this function without comparing it to anything else, could we do it? Could we integrate this function directly? Yeah? How would we do that? Yeah. So the antiderivative of this thing would be arctan. Yeah. So I like the suggestions you people have told me. I prefer to integrate simple things rather than complicated things. But if somehow you didn't notice that and you just thought, okay, this is the function, I gotta have to integrate it, that's no problem. You can also integrate this, right? So since arctan, oops, of x is the antiderivative of f, then if we want to integrate this thing, integral from 1 to infinity, f of x dx, it's equal to the limit as r goes to infinity of the integral from 1 to r f of x dx, which is equal to the limit as r goes to infinity from r to 1, arctan. And what's this? This is equal to the limit as r goes to infinity of arctan of r minus arctan of 1. So I'm following the book solution just because hopefully you're also reading the book, and just to show you what they do and why it's valid. Then you know what the limit of arctan of r is. By this point, you all got to be happy with arctan. Looks like this. This is pi over 2. Arctan of 1 is just pi over 4. So this is just pi over 4. Let me just put it over here. This is just pi over 4. And that's easy. And then that's more than effort than we need to do. So if it was a free response, again, I would be totally happy with you saying this is less than sequence 1 over n squared, and therefore we just need to compare that to the integral of 1 over x squared. And then you could just say by the p-test, the integral of 1 over x squared converges because p is 2 is bigger than 1. Yeah, so no need to do this extra calculation unless you don't think of reasoning this way. But if you want to, we can still answer the question. Okay, that's easy. Oh, I hope so anyway. How do you people think? Does that seem straightforward to you? Yeah? Okay, let's do this one. Example 2. For what values of P does the series sum k equals 1 to infinity, well, let's use n since we're using n before, n equals 1 to infinity, 1 over n to the p converge. Okay, solution. By the integral test, let's call this thing star. Converges if and only if the integral from 1 over 1 to infinity of 1 over x to the p converges, and we've learned this very well at this point, and this is true if and only if p is bigger than 1. Yeah? Cool. So we would cover this result that we had before, that if we just have the series 1 over n, it diverges. Yeah? And for sure, if we have a p which is between 0 and 1, then it diverges. Yeah? Because it's above the sequence 1 over n. And if p is bigger than 1, then it converges. Yeah? Cool. So this is very strong because just as with improper integrals of type 1, I told you look at it and compare it to the critical case of 1 over x. And if it's in a power way underneath 1 over x, if it's something like 1 over x to the p for p bigger than 1, then you'd expect it to converge. And if it's above 1 over x, then for sure it won't converge. Yeah? You can apply the same principle to this series, and that's going to save you a lot of time, a lot of possible confusion. So the case of 1 over n is the critical case. If we have a sequence of terms decreasing in a power way faster than 1 over n, it's like something like 1 over n to the p, where p is bigger than 1, then it's going to converge. Yeah? And if it doesn't, if it's above 1 over n, then we don't expect it to converge. Yeah? Or if it's going down to 0, like 1 over n, then we don't expect it to converge. So if you get very happy with this particular key example, 1 over n, then you're in good shape. You'll be able to quickly answer a huge number of questions where we'll teach you other methods to answer it, and there'll be other things, but you'll quickly get the right answer just from comparing it to 1 over n to the p for p bigger than 1. Yeah? So if you get very happy with this key example, this key critical case, just as those of you who've become very good with this key critical case of 1 over x, you will save yourself a lot of time, a lot of confusion. So good thing to have this firmly in mind. All right, let's do this example. This is example 4. Does the series n equals 1 to infinity log n over n converge? Okay. What do you think? Anybody else? Any other suggestions? Okay, okay, so you're comparing this to 1 over n. How does this series compare to 1 over n? What's the relationship? Yeah, can you give more information? Is there some more thing you can say about the comparison between the series 1 over n and the series log n over n? Slightly larger. Yeah, slightly larger. Yeah. And as you say, log is incredibly slowly growing, which is true. Yeah. But nevertheless, it is actually growing, right? Log n over n is not going down to 0, it's getting bigger. Yeah? So if we compare, so I'm going to show you two solutions. So compare the terms log n over n to 1 over n. We see that log n over n is actually bigger than 1 over n for all n bigger than 3. Because log of x for x bigger than 3 is bigger than 1, right? Log is very, very slowly growing, but it is growing, right? So from 3 onwards, it's bigger than 1. Well, actually, from e onwards, it's bigger than 1, but let's just say 3, because that's an easier number. All right, so why is that telling us good stuff? Let's visualize it. Yeah? Let's visualize it. So this collection of blocks is our series, right? So this is our series where the height of each block is given by log n over n. Yeah? Now, if I was going to draw on this picture the series given by 1 over n, what would I be drawing here? A box under the box. Yeah, so actually let me label these guys. So this is our series log n over n. I should not specifically point to this one. This is log n over n, this series, or this collection of blocks. Because of this, if we draw the blocks 1 n over n, if we draw the blocks 1 over n, then they are underneath, right? They are underneath, at least if we start counting from 3 onwards. So let's say that this here is 3. So this here is 0 and this is 3. So we're counting from 3 onwards. Yeah? Do you see what I mean, people? Yeah? Cool. So we know that the area underneath the 1 over n blocks is infinite, right? Yeah? And since these guys live on top of it, then that has to be infinite too. Yeah? Yeah? So just by comparing these guys, visualizing what it says, we know for sure the answer. We know for sure the answer before doing any calculation. Yeah? And that's what I want you to do first. I want you to first visualize the information. And think about the key case of 1 over n. And if you think about the key case of 1 over n, you'll all come up with this after a few seconds. Yeah? And if you draw this, then you'll see that the guy you're interested in lives above the series 1 over n, and then you can't get it wrong because you know that the area underneath the series, or you know that the sum of the series 1 over n is infinite, which is the same as saying the area of all these blocks is infinite, and you see that these blocks are containing the blocks whose sum is infinite. Yeah? Yeah? So there's no getting this wrong if you visualize this first. Yeah? Okay, but let's use the tool that we've learned. So I'm going to raise the board, and then we're going to use the tool, which is to find a function that recovers this series. So what function would do that? And du by dx is 1 over x, so we pick up this structure x over dx. Huh? So now let's use the integral test. So we already know the answer, right? So this is a double check, which is something which is very good to do because multiple choice has no mercy. If you understand things very well, but you make a slight little algebraic mistake, you get 0 points. So good to have some reason why you know the answer before you do any calculation. Huh? All right, so f of x equals log x over x using the integral test. So integral test will be abbreviated to int.test. The series converges if and only if integral from 1 to infinity of log x over x dx converges, and then we let u be log of x du by dx equals 1 over x, du equals dx over x, and then we just change this integral around. So we're going to have, when x is equal to 1, we have 0. So we're going to do the limit as r tends to infinity. And okay, let's do this in more than one step. So 1 to r of log of x over x dx. That's the limit as r goes to infinity. Change it around to u, so we go diverges even more. Yes, of course. Thank you. Thank you for that. Okay, cool. So, actually applying this to actually determine if something converges or not now becomes pretty easy, right? This is only going to work for series of sequences of terms that decrease, that are positive terms that decrease. Yeah. Now we're going to talk about some other powerful thing that this test gives us, and that's the ability to estimate the error. So this starts to enter newish territory for you, because up to now you've spent a lot of time explicitly calculating things, finding the explicit answer. As you go further into math, you find that there's less and less possibility to explicitly find an answer. That's a kind of a gift when you have a situation where you can explicitly find the answer. If there's a way to get an approximate answer where you can get the approximation to within whatever error you want, that is just as good. That is just as good as finding the actual answer. Yeah? Because for all practical purposes, you don't need to have the exact infinite decimal expansion of your precise answer, right? We live in a finite world with finite precision, right? If you can get an answer to within whatever error you actually want, no matter what you're doing, that's good enough. Yeah? That's going to be good enough. No matter how precise a thing you're building, no matter what the error tolerances are, if you can calculate within arbitrary precision, that's just as good as an actual answer. Yeah? And that's what you do more and more in maths as you go forward, particularly you as an engineer. You will be able to actually approximate your answer with better and better precision. That's some subject called numerical analysis. And I mean, there'll be two kinds of answer. There'll be those that you think is precise, and but you don't really know, and those you can actually show is precise. And obviously the latter is better if you can actually show it's precise and know exactly how precise it is. And that's what we're going to do here. That's what, perhaps it's a new thing for you, but that's what we're going to learn from these kind of ideas. And this is called the integral test error estimation. Integral test error estimation. Okay, so let's define our terms. So we can only live a finite amount of time. We can only do something finitely many times. We can only sum the series of the terms finitely many times. So the only accessible thing for us is the partial sum Sn, which is the sum from k equals 1 up to n ak, right? So if you're running a computer where every iteration you add the next term, then if you run it n times, you'll get this thing. This will be your approximate answer. But you would perhaps want to know how close this thing actually is to the actual answer, which will be given by the infinite sum. Yeah? So let S be the actual answer, which is the infinite sum from k equals 1 to infinity ak. Yeah? This thing is inaccessible to us because life is finite. So the best we can do is just take very large n. But we might want to know how close this thing is to this. So define Rn to be the difference between the two, S minus Sn. And then what will that be? That is just the sum from k equals n plus 1, capital N plus 1, to infinity of all these terms, right? Let's draw a picture. So this is our first block, this is our second block, this is our third block, and so on and so on and so on. Right? This, say, let's just keep drawing some things. Let's say that this is the nth block. So this is the first, this is the second, this is the third, this is the fourth, blah, 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 and say this is the nth block. Yeah? So the area of these first n blocks is exactly Sn. Yeah? And then as we go forward, then that thing is the remainder, right? So here is 2, 3, 4, 5, 5, so we're just doing dots at this point. And this thing here is n. Yeah? This is the first, this is the second, there's all these guys in the middle. The nth block is the thing that goes between n minus 1 and n. Yeah? And then all the other guys, I'm going to do in red here, are these guys here. Yeah? So all the guys to the right of this number, capital N, these are the Rn, the sum from n plus 1 onwards. So this is the nth plus 1 block right here, and we sum all of these guys onwards. Yeah? You see what I mean? Yeah? Cool. So what we want to do is to estimate all of these guys. We want to estimate all of these guys, because the difference between the actual answer, which is the area of all of this infinite collection of blocks together, and the finite answer, which is the area of the first n of these guys, yeah, is just the area of all of these guys going off to the right, these red blocks. Yeah? Once again, the difference between the actual answer and the first n blocks is all of these guys going off to the right. Yeah? Cool. So we want to estimate all of these guys here. Let's blow up this picture. So take this circle, blow up this picture over here. So what do we have? We have, this is up to n plus 1. Sorry, this is up to n. If you need to leave at any point, as always. This is up to n, and then we go to n plus 1, and then n plus 2, and so on and so on and so on. Yeah? Let's do some more, n plus 3, and all the way off to infinity. So these are all the guys here that we would like to estimate. We want to bound them from above. We want to know what the sum of all of these guys is. Yeah? Obviously, if the series converges, then that sum is finite. And as we let capital N get bigger and bigger and bigger, then this thing gets smaller and smaller and smaller. Yeah? Yeah? And we'd like to have some idea how big this is, because that will give us the error estimation. Yeah? That'll give us the error estimation. Knowing the size of Rn exactly tells us how far Sn is from the actual answer. Are you with me here? If I can write this in words somewhere. We need to estimate from above Rn. Yeah? That's what we need to do the thing that I said we want to do. Estimate the actual answer by the finite answer Sn. Cool. All right, look at this picture. What we've been doing so far is we've been taking our function f that recovers our sequence, and if we take our function f that recovers our sequence, it looks like this. Yeah? It looks like this. Yeah? So let's draw it here. It looks like this. Yeah? So, can you think of some calculation we can do that would estimate from above the area of all of these remaining blocks? This guy, this guy, this guy, this guy, all the blocks, n plus 1 to infinity. What calculation could we do? What integral? Integral from what to what? integral of the recovering function from n to infinity. Perfect. Because if we look at the integral from n to infinity, that thing is exactly the area of the function from n to infinity, and that thing exactly contains all of our remaining blocks, all of our Rn. Yeah? All the blocks in Rn. Yeah? Everybody see it? Yeah? Give me some feedback. Yeah? So the integral of the function from n to infinity is exactly this thing here that contains all the blocks we're trying to estimate. Yeah? Yeah? Cool. So from the picture, we see that Rn is less than or equal to the integral from n to infinity f of x dx. Yeah? And that's something we can explicitly calculate. Yeah? Cool. So this is very powerful because if you are doing some particular calculation and the answer is a series and you can't explicitly know what the series is summing to, and there's very few techniques that allow us to do that. It's only for geometric series or telescoping series. We can at least get within arbitrary precision. Yeah? So if you need to build your bridge within 2% error, you can find that, yeah? Because you can estimate the error with this integral. This integral we can calculate. That's the point of this. That's why this is powerful. And this, again, is not a difficult thing. It is just a picture. Just draw this picture. Yeah? Yeah? So the approximate answer is the first n blocks. I should perhaps write first, second, third, and so on. This is the nth, right? So the first goes from 0 to 1, the second from 1 to 2, blah, blah, blah. The nth from n minus 1 to n. Just draw those n blocks. Yeah? And then what's left? Then it's all of these guys to the right of n. Yeah? And all of these guys to the right of n, you can estimate from above by integrating from n forward. And that's it. Again, not difficult, not deep, not something to be memorized, not something to get wrong. Yeah? So pre-pandemic, one of the most common things was people trying to memorize this formula and getting it wrong. I claim there's no way to get it wrong if you actually draw this picture. And if you write the wrong formula, then you're going to get the wrong answer. But this thing is clear. It's just this picture. Yeah? Cool. There's another subtlety, and this is less important, but it is part of the course. You'll have homework problems on this. Sometimes we want to know a lower bound on the error. Yeah? So it's of less practical use to know a lower bound of the error. Usually we want to bound it above to know how close we are, but sometimes we want to know how far away our approximation is with a lower bound on the error, right? So if we have all of these blocks like this, can you think of a calculation that would allow us to estimate from below what Rn is? Think about what we did before. Perfect, perfect. You guys are doing fantastic. All right. Yeah, we're going to do exactly the game we did before. So this function here is the function f of x that recovers our sequence, yeah? Which lives on top. But what we learned was that if we define a function, I'm trying to find new colors here. Can't really find them. If we define a function g like this, so this is our function g, of x, where, so I'm writing backwards here, g of x is equal to f of x plus 1, then that thing is exactly underneath the blocks. Yeah, that's exactly what we saw before. Yeah? So that means that we can actually estimate from below what the error is, just by integrating this function g from n onwards. Let's put that somewhere. Putting this up here. So from picture, we see that n is bigger than or equal to the integral from n to infinity g of x dx, which is the integral from n to infinity f of x plus 1 dx, and by changing variable, that is just the integral from n plus 1 to infinity f of x dx. So we can bound below the actual error. We know that the error will have to be something, and we can have some estimate of how big it is. Yeah? And you can imagine there might be some situations where that's useful. Yeah? That's useful. Or at least it's you might be curious as to how big an error you're actually making. Yeah? So we bound this thing from above, the more useful thing, with this integral, and we bound it from below by this thing. And obviously this makes sense. This integral is bigger than this integral. Yeah? Because we're integrating over something longer. N to infinity is longer than n plus 1 to infinity. I guess that sounds really strange because they're both infinite length. Okay, let me say that better. The interval n to infinity contains the interval n plus 1 to infinity. Yeah? So this makes sense, that this is a lower bound and this is an upper bound. Are you all with me here? Give me a thumbs up. Okay, cool. So this is something people tend to have problems with. This seems to be a topic that is somewhat far from things you've done before coming here and learning university level calculus. And many students find this confusing, but I claim it's not. It's just pictures. If you're happy with the pictures, then the actual mechanics of doing the calculation is just doing an integral. So we're going to do an example of that, and then we'll be done for today. This is example 5. So I'm only going to do part B, where we're going to try and find an answer to within a particular precision. So this is the question. How many terms are needed to approximate this infinite series, the sum from k equals 1 to infinity 1 over k to the 3, to within (0.0005). Okay. Solution. All right, so it might look like a very hard question, but it's not. It is not. It is a straightforward question because we have the tool, right? Let's visualize it. We have a collection of blocks. And so on and so on and so on, right? This is 0, this is 1, and so on. We know that the first n are these guys, yeah? So it's actually, I'd like you to draw a picture whenever you use the integral estimation test, because that way you're not going to get it wrong. Yeah? So draw a picture of the first n, yeah? And then draw in a different color what the remainder are. Yeah? So all we need to do is to find the n such that all of these guys, which are to the right of n, yeah, have total sum of their areas less than this thing. That's all we need to do. We need to find the n such that all of the areas of the red blocks to the right of the n is less than this. Yeah? With that picture in mind, this seems less intimidating, right? Because what is this given by? So let f of x be this function 1 over x to the 3. Yeah? Draw that. So that means that your function is this thing. Yeah? And then you see from the picture that what you need to do is to estimate these remaining blocks by the integral from n to infinity. That's the statement of the theorem, but let's just draw the picture so we know what we're doing. So Rn, which is the sum from k equals n plus 1, right? The n plus 1 blocks, because all of these guys in green are the actual n, the actual terms of Sn. So the remainder are from k equals n plus 1 onwards of this 1 over k to the 3. And we know, because we can see it, that n is less than the integral from n to infinity of this function that recovers, 1 over x to the 3 dx. Yeah? So let's write in words and math what we need. So we need to find capital N such that the integral from capital N to infinity, 1 over x to the 3 dx, is less than this thing. Let's put here, can't fit it in. Is less than 0.0005. That's what we need. Yeah? Now that we've expressed our problem in the language of math, now this is completely tractable, right? This is a completely tractable thing. Yeah? Because this is something we can explicitly calculate. Yeah? And what is this thing? Integral from n to infinity, 1 over x to the 3 dx, is the limit as r goes to infinity of the integral from n to capital R of 1 over x to the 3 dx, which is the limit as r goes to infinity. And the r, what's the antiderivative of this? Let's try this thing. If we differentiate this thing, we're going to get a minus 2, which is not what we want. So let's put a minus 1 over 2. If we differentiate this thing, we are indeed going to get this thing. Yeah? Okay. Let's pull out this minus a half. And then this is the limit as capital R goes to infinity of this. N to the R of x to the minus 1 over 2. And that's minus 1 over 2, the limit as R goes to infinity of minus 1 over r squared minus 1 over n squared. As r goes to infinity, this thing just vanishes. So what we get 1 over 2 n squared. Yeah? Everybody happy? Everybody with me? Yeah? So now let's rephrase what we need. Yeah? So need n such that 1 over 2 n squared is less than this thing. Let's actually write this as a fraction. So we know that 0.5 is the same as 5 over 10. 0.5 is the same as 5 over 100. 0.05 is the same as 5 over 1,000. So finally, 0.0005 is the same as 5 over 10,000. Maybe you can do this instantly, but I always want to check it. Yeah? So we want this so that this thing is less than 5 over 10,000. Like this. No? And now that's a completely tractable problem because we can just rearrange the stuff, right? So let's multiply the 2 on the other side. So that's going to be 1 over n squared is less than 10 over 10,000, which is the same as 1 over 1,000. And then let's multiply stuff, rearrange it. So we're going to have 1,000 is less than n squared. So what we want is actually the first integer such that n is actually bigger than the square root of 1,000. Yeah? Obviously, we don't want to do more work than we have to do. We don't want to sum more terms than is necessary because it's asked us to get the precision to within this. You know, we could if we took the n that solves this and then added another 5 million terms, then that would have more precision. But this would be, if the practical purposes, this would be more computer time, more cost. The customer has asked us for this level of precision. We want to do this as economically as possible. So we want to find the smallest integer for which this is true. Yeah? And when you ask this question, it's no good to find an n that will do this. You have to find the smallest natural number that will do this. Yeah? We don't want to do more summing than we actually need. So the square root of 1,000 is 3.61, or more or less. So square root of 1,000 is up to the first natural place is 31.6. not what I originally said, 31.6, right? So the smallest integer that is bigger than 31.6 is 32. Yeah? So now we know that we just need to sum the first 32 terms in order to get an answer to within 0.5. So let me put it over here. So S of 32, which is the sum from k equals 1 to 32, 1 over k to the 3, that's a completely tractable problem, right? You can type this you can program this into any language you want, right? Your computer will give you this within a millionth of a second. This is very easy to calculate, yeah? Yeah? This thing is within 0.0005. Yeah? Cool. So this actual sum here, which you can't actually answer, this isn't a geometric series, it's not a telescoping series, we can't actually tell you what this is, at least with the techniques I've taught you. Yeah? But we can get the answer to within any precision you like, rather easily using these rather natural, simple geometrical principles. Yeah? Yeah? This is power. This is real power. Cool. All right. Is everybody happy with this? Excellent. All right. Now we have office hour. Stick around if you have any questions. Otherwise, I'll see you all on Friday.